Thank you. Let's see if I can trip over it on the way. Yeah, we're live. Thank you for coming to BIMI for another Tuesday evening talk. Tonight, we're really thrilled to have Bryan Oakley here. Bryan is a wonderful friend of Block Island. He's been studying Block Island in his geological and coastal research for 25 plus years now. Okay, he's too young for that, but 20 plus. Anyway, and it's ever since Superstorm Sandy, starting in 2013, he's been profiling the beaches and studying the shoreline changes around Block Island. He is the most knowledgeable person that I can think of in terms of what's been happening here around the island. And he's going to talk to you about that tonight and also share with you some of the things you can do to check it out for yourself so you can see what's happening around your properties and who you want to buy out. I don't know. Well, he won't go into that. He doesn't touch on that. He stays at a much higher level. But I will tell you, after seeing his work earlier, it's just fascinating. Now, I'm a geologist, so okay, I'm a little biased, but you'll love it, not any doubt. So thank you for being here. Without further ado, Dr. Bryan Oakley.
I think I learned tonight. Can you guys hear me? Good. I think I learned if you really want to draw a crowd, you have to research sharks. So Jasmine, you're in the right field for a crowd. Now, thank you for coming out. It's a lovely evening. What most of you guys don't know, including the people I've been working with now for a decade, is I started my public speaking career as a tour guide on a tour boat in Newport, where I would spend an hour saying off to the right is this. So off to my left is the screen, and I'll try not to stand in front of it, and I'll try not to trip on the mic. One of our hallmarks at Eastern, that's where I work, is Eastern Connecticut State University, is small class sizes. So I don't usually lecture with mics. So this will be a challenge. Now, I'm the only name up there. I work with a whole host of people. I'll introduce a bunch of them a little bit later in the talk, but a lot of these drone or helicopter images were actually shot by my colleague at Eastern, Drew Hyatt. He and I work on some of the more recent bluff erosion topics, and you'll see some photos from him. And I've had a whole cadre of students over the years work out here on and off going back to 2013 or so. So I'm going to try not to make this too much like school. If you know that reference and know that movie, you and I should be friends. We're going to try to keep this a little bit loose, and I'll try not to make it a super dry lecture for you. So before we get into shoreline change, I thought we should get into our Wayback Machine and jump into another aspect of work I had done way back as a grad student, looking at the impact of kind of how the island got here and when we would have had shorelines. So Block Island sits near the terminal margin of the Laurentide ice sheet, which extended over much of northern North America, reaching its maximum extent between 26 and 28,000 years ago. If you had 18,000 in your head, throw that out. Science has gotten a little bit refined since then. It's older than that, 26 to 28,000 years ago. If you wanted to come to Block Island and you wanted to go to the beach, you of course had to go out there because global sea level was 400 feet lower. To make a giant ice sheet, you need water molecules. There's only so many on the planet, so the water comes out of the ocean to make the ice sheet. So we were sitting there at that little red star. I can't use the laser because it's a television screen, but you can see that little red star. Now, Block Island is what's called an interlobate moraine. It means it's not quite the terminal moraine of the Laurentide ice sheet, but it sits where two chunks of the ice came together, and that gives it this kind of north to south pile of stuff down at Beacon Hill Moraine and then up to the north at Corn Neck Moraine. So when did we start to have a shoreline? Well, as the Laurentide ice sheet started to melt, every little depression or hole would have had water in it, right? The Laurentide ice sheet melted with billions of gallons of water. Again, global sea level was down 400 feet, mostly because of that ice sheet. So there's a little early thing of glacial Lake Block Island, a figure from now 13 years ago. I still mostly believe these, I think. So there's Block Island off on the right. That was part of a larger glacial lake system. Glacial Lake Connecticut and Long Island Sound probably was separate, but Block Island, Rhode Island Sound, and Narragansett Bay all had lakes. There were probably one big lake during deglaciation when the ice was up north of Providence somewhere. Now, we know this because in that under Long Island Sound and Block Island Sound and Narragansett Bay, you find these things called glacial varves, very distinct for freshwater glaciers, not in the marine environment. And turns out people have known that for 60 years, that that's a glacial lake back then. So way before marine shoreline, we had a glacial lake shoreline. Now, as I said, sea level was much lower. We'll talk about how fast it's coming up today, but it's not the fastest we've seen in recent years, geologically recent years. There were stretches there in the middle where it was rising well more than a meter per century in the middle part of kind of the breakup of the Laurentide ice sheet. So as sea level rose, we of course would have flooded the continental shelf. Now, we made these figures when I was working with John Boothroyd. Again, I probably still mostly believe them. Huge caveat though, we're not modeling erosion or anything. We're just playing with the colors to show what might have been a lake and what might have been ocean. So this is about 11,500 years ago, 11,000, hey, 10,000. Once we get to this magic number that sea level is about 30 meters below present, we probably actually had an island. That's probably when Block Island was separated. Maybe it hung on a little bit between Montauk for a while, but that's probably when Block Island became an island, at least the first time. Maybe 9, maybe 10 and a half, somewhere around there, 1,000 years ago. And that's not far off from other estimates. This is Oswald's paper working with Dave Foster at Harvard. They were looking at Martha's Vineyard and Nantucket, and they became islands a little more recently, probably more like 7 or 8, 10,000 years ago. Excuse me, 7 or 8,000 years ago, because they're shallower around it. So we've had a shoreline for, let's say, 10,000 years. Okay, back to the future. I'm going to make another shameless plug. If you want more information about this, you should get Dennis Zambrata's second book. I wrote a chapter in that book during COVID. It was actually pretty cathartic to kind of brain dump a lot of this out. And Dennis is the speaker next week. So if you're on the island, Dennis and I have been friends since I was 7 years old. It's worth checking out if you're interested in surf casting and history of surf casting on the island, and buy his book. Okay. So let's jump ahead to think about the island today. And when we think about the island today, we think about the island being 2 pieces of glacial end moraine: the Beacon Hill moraine to the south, including Mohegan Bluffs, the Corn Neck moraine to the north, and it's connected by a series of what we call barriers. And these barriers are just that. They're barriers between water and the ocean, right? That form from coastal processes and separate, in this case, Great Salt Pond, Middle Pond, and Sock'em Pond from the ocean. And then we also have the bluff shorelines. And everybody who's been on the island has seen the bluffs, whether it's just coming in by the ferry and then going straight to Ballards, or whether it's actually exploring the island. You've seen the bluffs, right? They range from barely there on the west side to obviously the Mohegan Bluffs and the really high bluffs on the south side of the island. So when we think about the shoreline change of the island, we need to think about both types of shorelines. So I go with the Army method of giving you a talk. I'm going to tell you what I'm going to tell you, then tell you it, and then if there's time, I'll tell you it again at the end. Now, if you're had a big dinner, you're ready for a nap, after these next 3 slides, you can go to sleep. Just remember these 3 slides. Everything else will be details around that. So our first key point we want to hit tonight is storms are the most important driver in coastal change. If you're in my class right now, it's a stop, underline twice. That's going to be on the test. Right? Sea level rise amplifies that effect of time over time, but if you're thinking about what's actually moving the sediment, it's storms. When we think about the bluff shorelines, we need to think about how they change. And it turns out that's not just waves. We were to go walk around the island today after this heavy rainstorm, we're going to see sediment moving around as surface water moves across the bluff face. So we need to think about the other ways bluffs erode. We could talk about how we measure bluff change and how much they've changed over the century time scale, going back to 1886. And the average around the island is 20 to 30 meters. I'll try to get English units in there when I can, 60 to 100 feet or so. Okay. And then bluff erosion rates in the more recent time period were higher than they were over that long time period. We'll talk about why. And we'll talk about how that feeds the overall sediment budget, right? Bluff erosion looks bad, but it's actually got some benefit. And then we'll close thinking about the beaches, that they're dynamic, how they've changed over the last decade. Dunes recovery largely from Sandy, and they recover slowly. West Beach continues to erode, and then we'll close with that none of this gets better in the future. I'll leave you with a really positive note. Right? So there is one elephant in the room. When I put up a bullet like storms are the most important driver in coastal change, everybody who follows this at all, his first instinct is to go, well, what about sea level rise? Sea level rise is obviously the elephant in the room, or it's to set up the time of the penguins. It's important. And we need to recognize that sea level is rising. We measure that multiple different ways. And this comes out of a NOAA report that projects out to 2050, somewhere between 40 and 50 centimeters of sea level rise, foot and a third to almost 2 feet above the year 2000. That doesn't sound like a lot until you go stand around a harbor at high tide and picture another 1 foot or 2 feet on top of that. NOAA in this report only goes out to 2050 because of the uncertainty around the Laurentides and past, the Antarctic and Greenland ice sheets, and what their dynamics will be in the second half of the 20th century or 21st century. So they're just not comfortable making those projections. So they're planning out to 2050. And there are places in the country where sea level rise is a huge issue now, right? This is Ile de Jean Charles in Louisiana. It's now a little bit older piece by Coral Davenport in the New York Times, talking about resettling the first kind of sea level rise casualties, if you will, in Louisiana, and the fight about people who don't want to leave, even though they're getting flooded out. Now, the island itself is lucky. A lot of the island has pretty good elevation capital, right? Because of the moraine stratigraphy of the island, it's pretty high in a lot of cases, but that doesn't mean there aren't low-lying areas that need to be considered. This is 3 feet of sea level rise plus a 25-year storm. That's a Sandy type storm. Again, I guess I can use the laser pointer on the screen here. No, I can use this laser pointer. Right, so here's Old Harbor, right, and here's Great Salt Pond, and you can see where you've certainly got some issues along Corn Neck Road in that scenario, right? If we want a sneak preview of what that looks like, right, you just have to look for storms, because storms give you a nice sneak preview of sea level rise, and we can watch this one from a very familiar landmark.
This is the approach to Bimini. It's high tide, right about 9 a.m. on January 13th. As you can see, parking lot is flooded, but it looks like it hasn't gotten up into the building, which is really good. But the back 40 and the parking lot totally flooded. Here we are at Bimini, January 13th. 9 a.m. high tide.
Yeah, that was this past January. Our own Judy took the video. That's 3.5, 4 feet of sea level rise every day. Now, of course, being on the island, you have to consider other areas, and the bigger vulnerability, or one of the bigger ones, is of course Galilee, which is very low lying, built on basically filled marsh, and has a very low elevation, and certainly is a vulnerability, both storms and sea level rise for the island. How much is it rising today? Well, Newport tide gauge going back to 1929, it's about 3 millimeters per year. It's about 1 centimeter every 3 years. Although some authors would argue it's probably closer to 4 millimeters or maybe a little higher than that. There's some noisiness in that blue line over time. Some of that's things like El Nino or La Nina, change sea level over a year or two period. That's that most recent uptick you see is last year's El Nino year. So it gets to be a little bit of a game drawing those regression lines, but we're somewhere in that neighborhood. We're not as high as Louisiana. We're not as low as other parts of the country. The reason I focus on storms is if we think about normal high tide and low tide as those blue lines on this little ruler, Sandy's way up there, 4.5 feet above high tide, and the 1938 hurricane's 9.5 feet above high tide. So whether sea level is coming up at 4.1 or 4.3 over the next decade or two, it's going to have a big impact in low-lying areas. But when you're adding it on top of those storms, it's signal to noise kind of ratio. So where do we look for storms? Well, our most recent kind of impactful storm, these past winter storms had a lot of flooding, but not a ton of erosion, was Sandy. Sandy was a geographic monster of a storm. It merged with a cold front, became this huge weather system, impacted the entire northern eastern seaboard in the same few days, right? Coastal erosion in New England, snow in the Appalachians at the same time from the same storm. And because of its size, its intensity, and its track, had a fairly high surge for its category and had big waves. The offshore buoy at Block Island, which is south and east of the island, about 15 miles or so, recorded wave heights of 9 meters, about 30 feet, which meant the largest individual storms might have been 40 feet or more if you play with the math a little bit. We actually almost got there in this December 2023 storm. Not quite as high, but it was close. That led to erosion of infrastructure around the island, right? Corn Neck Road was impacted, right? And sediment was transported across the barrier, because Corn Neck Road and Crescent Beach here is a barrier, not a bluff, right? And all that sediment you see labeled wash over fan, right? That was out here on the beach or in the dunes, and then it washed across the road. And while that is a problem for infrastructure, right? That's the actual natural response of how these shorelines respond, right? Barriers want to move landward and upward, right? If they went to yoga class, that would be their mantra, landward and upward. They're moving back, they're moving up. And you can see this really well illustrated here. If you've been down over on the west side, that's New Harbor Inlet on the right-hand side and Great Salt Pond up here, right? This is Bean Point. Bean Point's a very small little, it's what we call a drumlin. It's a pile of glacial till. And next to it is this big salt marsh on a barrier spit between there and West Beach. And what you see labeled is a washover fan. That happened during Sandy when the sediment on the beach was pushed back across the marsh during the storm. And if you don't believe me that happened in Sandy, right, we can look at other places where it's happened in the past, including Middle Pond, which was overwashed heavily in the 38 hurricane. But let's go back to this area of Bean Point for a second. This is a June 2012 photo. It's before Sandy. That red line is drawn along what we call the high tide line. It's the wet line from the last high tide swash. And that's before, and that's after Sandy. I didn't move the red line. That's just what changed. So that's the shoreline retreating. And that's what barriers are supposed to do. They move back, they build themselves up. And so if you're a salt marsh ecologist, you know, you're having a fit that some of your salt marsh is buried under 2 feet of sand here, but that's your future salt marsh in a couple of decades. So it's all good. That's what the barrier is trying to do. The challenge we have, and not just on the island in general, is we like to build on barrier islands and barrier spits. Think New Jersey, think Mesquamaket, think all those places. And that does tend to fix them in place. Here, nothing's fixed in place. This can kind of do its own thing. Okay, let's get off the barriers and let's go to the bluffs for a second. Any bluff that you can think of in the world that's eroding kind of falls into somewhere on this triangle. Right? Some bluffs where it's maybe low energy, you're on a river, you're on a lake, maybe it's more surface water, again, like today with the rain, or groundwater driven. But if you're in a coastal setting, you have to factor in wave erosion when you think about how your bluffs change. And so we're going to think about bluffs changing with those 3 different processes that all do the same thing. Whether it's waves impacting the bluff there on near Southwest Point, whether it's groundwater seeping out of the bluff face or surface water running across the bluff face, all of those work to take sediment from the bluff and bring it down to the beach, right? And the cumulative effect of that is that the bluff will retreat or move backwards. So the metric we use for that is we measure the bluff crest, right? Where this break and slope is right at the top of the bluff, right there or over here, you know, anywhere you want to see the bluff edge. We can map that out and measure how that changes over time. Right? And it's a cumulative effect of these different processes. Right? And we can see it happening kind of all at once, and it's not happening in a vacuum. In some areas, waves are going to be more important. In others, it's a combination of them. So this is up by Clayhead, again, a model by my colleague, Drew Hyatt. I think these are his drone images, but that could be the helicopter. I can't remember. And you can see where there's these little valleys we call rills, and there's some bigger ones over here. That's where surface water and some groundwater is carrying sediment down the bluff face. And then down here at the edge, we see where the bluff face has been cut back by waves. So when we think about the change in the bluff, right, the waves aren't removing sediment all the way up here at the top, right? The wave erosion in Sandy we measured kind of stopped somewhere where it actually caused the bluff to change around 10 meters. But once it removes some stuff down here, it can destabilize and allow the top to come down, right? So that's why we use the crest or the top of the bluff to measure that change. And this can be dramatic. And one of the things I want you to take away from this, it's not one of my bullet points, is shoreline change doesn't happen linearly. It's not like this is 1 year, here's another year, here's another year. It's just something where nothing happens for a while and then big jumps happen, often during storm events. So one of these happened in April or May of 2019. This is June 2018. I'll draw the edge of the bluff so you can see it in the back. And that's April 2019. I'll go back. You didn't notice that this whole chunk of the bluff here is gone. And for scale, the widest, depending on which way you do your arrow, is 20 or 25 meters. So 60 or 70 feet. And if you're not familiar with where that is, those rocks mark where Southeast Light used to be. Southeast Light's now just out of the image to the back. So pretty good idea. They moved the lighthouse back in 1993, huh? Took a little while, but it got there. And there was a couple of recent ones. This was, again, Drew's photos. One slump here and the other one here, not too far from the steps on the south side of the island. Not surprising. We had some big winter storms that eroded the toe of the bluff, and then it was the wettest spring on record in Rhode Island. So I'm not surprised we saw some bluff slumps, and frankly, I'm surprised we didn't see more of them. So how do we measure this stuff? We do tend to work in the metric system. I will try to put English units. I am not going to do armadillo-sized asteroids. If you're local, I did meet Jimmy, the golden retriever, last time I was out doing field work. He was my field assistant for most of an afternoon. So I guess we could have measured things Jimmy-sized, but we're not going to do dog-sized either. Right? Primarily, we use two data sets for this. Right? We use something called LiDAR. Right? LiDAR is airborne mapping done with lasers. So an airplane, typically an airplane, will fly overhead, shooting lasers, kind of like my laser pointer, right, off the ground surface, right? And knowing the speed of light, they can do the travel time for how long it takes the laser beam to go out and come back. And then they can use the GPS in the plane to figure out how far away the ground is and do some math that I don't understand and come up with an elevation model of the ground surface. And it's pretty accurate, generally vertically 6 inches or so. And the resolution is usually a couple square feet, give or take. So, if I moved my backpack and then did the survey twice, it might catch it that it had moved. So it's pretty accurate. And that's what these two panels on the right are, B and C. They show where the LiDAR is on the southeast corner of the island. And we go in and draw that black line manually, mapping the edge of the bluff. We're comparing that back to this really cool map done in 1886 by the Coast and Geodetic Survey, one of the early predecessors of NOAA. And they had mapped, if you're local, they call it the Stonewall map, this really detailed map of the island, including the bluff crest, the shoreline, and all of those stone walls. And the stone walls, because they haven't changed, allowed us to bring that map into real world, like modern coordinates, and measure the changes in the bluff over time. So we come up with a bunch of numbers. I know you can't read that. Let's summarize it this way, right? So we divide the island up into 4 little chunks here for this figure. Northeast corner, so Grove Point to Mansion Beach, Old Harbor to Southeast Point, Southeast to Schooner Point, and then Schooner up to Grace's Cove. Again, just focusing on the bluff shorelines. And the average retreat of the bluff varies a little bit, but for the most part, the northeast, south, and southwest sides are all about 30 meters, so about 100 feet of change over 130 years. So Chris said, oh, it's a foot per year. That's not far off. So all the locals that have been telling you that for 50 years, that it's about a foot per year. Not bad, not bad. The data backs it up. The low area is the southeast corner. I think that's an artifact of the geomorphology. If you walk that shoreline, it's a pretty gnarly walk in spots. There's a lot of what we call terraces where the gravel and boulders form really wide intertidal areas. I think that deflects enough wave energy to kind of lower that number a little bit. In parentheses, the numbers, the shoreline change, not the bluff. They're about the same number, right? Between the shoreline change maps and the bluff top. The highest we measured was down on the south side, 75 meters or 240 feet over that 132 years between Barlow's and Spar Point. We then compared it to 2 different LiDAR surveys in 2011 and 2018, and we found that the rates were pretty substantially higher over those 7 years than they were over the 132 years of the whole data set. And there's numbers up there. I'm not worried about knowing all the details, but basically half the transects changed by 1.5 feet in the recent survey, only 5% changed by that much per year in the longer term survey. Anybody want to hazard a guess or anything noteworthy happened between 2011 and 2018? Yeah, Sandy. Absolutely. So what we're really seeing is the influence of Sandy on the data, right? And it's not sea level rise accelerating. That may contribute to higher rates from now into the future, but in this case, it's Sandy, right? So the way I actually like to look at this difference in rates is if you think about the whole of the survey we have, 132 years, 13% of the retreat on average, not specific to any one spot, occurred in 5% of the time. So more of the change happened than it should have. Why? Well, when we think about shoreline change, it's very event driven, events being storms. And so I've got a very simple little graph here, no numbers on it, no scale, because it's going to depend on your actual shoreline. It's an old paper from Sunimura in 1983. Time is across the x-axis, and the amount of retreat, or how much the bluff is moving back, is on the y-axis. And what you'll notice is there's periods where there's not much change. The line's flat. And then you'll see there's an event, one of those red arrows, and things go back pretty quickly. Now, that pretty quickly might be actually during the storm. Some cases, it might be a year or two after when things kind of readjust. But it's a fairly steep line where there's a lot of change happening, say here, right? And then a period where not much happens. And then, oh, look, a little storm. And then a long time with not much happening. So when we look at that 132 years of data, we're really seeing it smoothed out into this kind of annualized average rate. When we look at it over 7 years, we're seeing that steeper curve, right? So it shows you what can happen in a short period of time, but it's entirely, in this case, due to Sandy. So where does all that sediment go that we erode from the bluffs? Well, it turns out bluff erosion, well, it's catastrophic if your house is near the edge of the bluff, is a big part of our coastal sediment budget. And this is a figure, it's in a whole bunch of geo textbooks and coastal textbooks by a guy named Paul Komar, now passed away, who's a very famous coastal geologist from Oregon. And his analogy was always, it was your checking account. Your debits, your paycheck comes in, right? That sediment added to your coastal system. And then your credit, what you're paying, goes out. So whether that's sediment going offshore, off, in our case, north off North Light and out into deep water, right? That's sediment lost to the coastal system. So one of the big credits we get is bluff erosion, because as sediment's eroded from the bluff, where does it go? To the beach. Now, not all of it will stay on the beach, right? Some of it, if it's mud, goes somewhere else, goes offshore, into the coastal pond, into wherever, to your, whatever your favorite spot to deposit mud is, it goes there, right? The sand and the gravel can stay on the beach. So when we see an event like this, and if you tried to walk around that slump right about here, you couldn't get by it. Now, it doesn't last long. The waves chew that up pretty fast, right? The ones that just happened in May and June, you can walk in front of them now, right? But that sediment goes somewhere. So if you've been out on the island after a storm and you're looking down from the top of the bluffs, and I'm a Rhode Islander, it looks like it's ringed by coffee milk, chocolate milk if you're not from Rhode Island, right? And that tends to screw up fishing, right? So no bass, right? I had a mistimed surf casting trip with buddies we did every year that came 2 days after Sandy. Got some great pictures of Corn Neck Road torn up. We drank a lot of bourbon. We didn't do a lot of fishing because the island looked like that all the way around. But where's that sediment going? Well, it's in the surf zone. So the stuff you see in there that makes it look like coffee milk, that's the mud. But the sand and the gravel that's in that deposit stays on the beach. And maybe it doesn't stay right there, but it can move along the shoreline and basically feeds the beach, right? It's kind of like natural beach replenishment when the bluffs erode. And we can actually quantify that. So if you had a particular slump or deposit, you could figure out how much sediment would get added to the beach by taking the amount of bluff retreat, the size of the bluff, and how much of that sediment is of the right size to stay on the beach. So I won't scare you with math. I know my students always go cross-eyed when I put too much math on the slide, but let's just do a hypothetical, right? If your bluff was retreating at 1 foot per year, the bluff itself was 30 feet high, and the slump you're talking about, or the area you're talking about, is 100 feet wide, and half of it was sand and gravel. And it would be about 55 cubic yards of sediment on average per year coming out of that bluff going to the beach. And then you have to think about the entire size of the island and do the math. It gets to be a pretty decent sized number. So the actual shoreline change rates on much of the island, particularly the east beaches in here, oh, sorry, my orientation's wrong, that way, right, are relatively low compared to areas we see in Matunic or even Mesquamacut, where shoreline rate rates are higher because there's just not a lot of sediment coming into the system like there is here. So in that respect, while the bluff erosion looks bad and scary, it does help the island beaches. All right, so speaking of the beaches, let's take a closer look. So I'm going to remind you of a couple of my more points. Beaches are dynamic. I'll tell you how we know that. Dunes recover slowly. I'm putting emphasis on that because I want you to remember that. They recover slowly. West Beach continues to erode, and then we'll get to the future stuff. So I'd be remiss without recognizing how we know so much about the beaches, which is the Block Island Beach Profile Crew. I'm thinking about it today when a previous meeting. I don't really have a good acronym for us. I guess the BIBPC. That doesn't really roll off the tongue. We'll have to keep thinking about it. This started, I don't want to say it started on a lark, but in 2013, I was out here with a couple of students. We were getting ready to do shoreline change mapping. So we spent 3 days circumnavigating the island, taking pictures and notes, just getting our heads, mostly getting my head around it. And then the last day, it was a day like this. And I happened to have my beach profile sticks in the back of my pickup truck and said, well, let's go set up a couple of beach profiles, with the idea being that maybe I'd come out once a year with students and measure them. And then later that summer, I was talking to Chris Littlefield at the Nature Conservancy, and Chris was lamenting that he felt like he was running a wayward home for retired scientists because Nigel, Kathy, Judy, and Jules had all recently retired full-time to the island. And out of that, the project kind of came to life, and they've been doing it ever since, now 11 years in. The new kid, George, came on in 2018 or so, and Claire and Tig and a whole bunch of other people have contributed to it. Now, unbeknownst to us, Dave Ankos, I saw in the crowd somewhere, had been doing a survey twice a year at Mansion Beach and heard about our project, I think the first year we were doing it, and graciously gave the data and the location to us and told us where it was. And we were able to get it into our kind of system of surveying and location and able to connect that up. So that's actually really valuable because it's the only profile we have that predates Sandy. The rest of them all started in 2013. So we measure profiles around the island, balancing access and shoreline types, right? Obviously, we're not walking, 2 miles from the steps around to the middle of the south side of the island. But we've got 3 sites active on the east side, Mansion Beach. There's actually 2 sites there. We'll call it 1. Scotch, Crescent Beach. We had one at Corn Neck Road, but trying to cross Corn Neck Road in June to profile was hazardous to their health, so we stopped that one. There's also really not much sand left in front of that revetment. 1 at Cunimus Road, 1 at Charleston Beach, and then 2 north of the inlet. The one at Old Cut in yellow kind of gets done when Nigel and Kathy feel like walking down there, usually to check oyster catchers. Now, this is done using something called the modified Emery method, and we started with monthly profiles. And that got to be a bit much, I think, on those guys, particularly in December when it's cold. But it was really valuable at first because it gave us detailed looks at how these things change. And also, I think the proficiency in the surveying went up really fast because you guys were doing it so often. And then we switched to quarterly profiles in March of 2018. So far, that's around 570 individual profiles surveyed. Again, collected using this thing called the Emery method. Lovely picture right there on just a balmy field day in probably February. Right. I have done a lot of field surveys like that, so I sympathize, but it's part of the game. Right. So Emery method is also known as 2 sticks and a string. It was invented by K.O. Emery, who's a very famous oceanographer around 1960, published it in 1961, and it uses 2 graduated sticks, survey rods originally, but we make our own, marked every 2 centimeters. And then, as my colleague Rob Hollis is demonstrating, Block Island's in the background. This is at John Boothroyd's very famous Chiuzi profile. We're seeing a minus 22 centimeter reading using the horizon as a level. If it's foggy, we have a hand level. And that measures the relative change in elevation from your starting point across the profile. Now, They get a lot of questions out here, particularly in the summer. Oh, what are you doing? That looks like a joke. It's extremely accurate and precise when it's done carefully. And we can check that against our GPS data, and we have, and it's spot on. So this allows us to see how the beach has changed over time. So this is a profile of Mansion Beach, the one in 2007 measured by Dave Vanko, and then 2024, June of this year, and then in red is 2013. And Nigel had a good comment earlier that it's hard to maybe see what you're looking at here. So let me use the laser pointer. This is the dune right here, this bump. Right now, it is a dune. I know you can argue about that later, Judy, but this is the dune. And this was the foredune crest or top of it in before Sandy. And then this retreat of the shoreline largely occurred during Sandy. And then it's come back a little bit, but hasn't seen a ton of recovery. And so the fact that there's white space between these two tells you that the shoreline has retreated back since Sandy, and it never quite came back to where it was. Again, not unexpected. That's what these shorelines tend to do over time. But because we did them monthly, we can actually hit play on this, and I'll click this one a couple of times. This is a year in the life of Crescent Beach. So it's labeled, but if you can't read it, this is the road. Our benchmark is actually a telephone pole. There's the parking lot. Here's a signpost on the back of the dune. And then this is the dune here. So when you're out on the beach, you're out on this part, and then you'd walk down this slope to go in the water. This is a July and August profile from 2016. We have data all the way up till now, but making these animations is a pain, so I haven't done a new one, but I'll hit play on it again. And what you'll notice is after storms, particularly in the winter, you'll see a flatter profile, kind of a higher profile in the summer, flatter again after some storms. And the beach changes a whole lot. The dune here and there, but not super perceptible at this 1 year time scale. But if we compare it out over 11 years, wow, that dune's changed a whole lot. So the two lines there are 2013, post Sandy, and then 2024, which was February of this year. And you see a whole lot of accretion. Basically, all of this was added to the beach in 11 years, or added to the dune, excuse me, including some on the back of the profile. Similar story at Scotch Beach, a whole bunch of dune accretion, a very narrow little eroded dune when we started the profile, again, after Sandy. It's recovered reasonably well. And we can actually quantify that. And this is where the profile data gets really valuable, because you can start to think about how long it takes to recover, right, after these storms. And when we're talking about a storm like Sandy, the 1938 Hurricane Carol, take your pick on historic storms, for the dunes to recover, you're talking a decade, sometimes more than a decade. And the reason is that looks like a fairly steep curve when I graph out the volume of the dune over time. But Scotch Beach grew at an average rate of just under 2 cubic meters per year. If you ever had material delivered to your yard, a couple of cubic meters or a couple of cubic yards isn't that much sand. Right? And that's what's adding to it over the course of 1 year. At Crescent Beach, it's a little higher. It's like 5 cubic meters a year. It's a pretty robust dune system, but that's still not adding dump trucks full of sand every year. It's happening slowly over that time. So it's always good to keep in mind that after these storms, the beach itself comes back fast. The dune takes a very long time. So let's close with a couple last things. West Beach continues to erode. If you spend a lot of time on the island, you're probably aware of this. If not, go down West Beach Road, take a right on foot. Can't drive in front of the landfill anymore. You used to be able to. You have to walk up that shoreline. And you'll see an area that's got the highest shoreline change rate of anywhere on the island. So this is a shoreline change map. George, thank you for the reminder. You can get these publicly available. They're on CRMC's website, Rhode Island Coastal Resources Management Council. You can download a map. There's 9 of them that go around the island that really, they print out at 42 inches wide. They're huge. So you can take a pretty detailed look at the island that way. And the black line on these maps is 1952. The green line is 2016. And then the little box tells you how much it's changed in black and how much that averages out to in white. Now, if you're not familiar with the West Beach area, I'll orient you. That's the landfill, right, or the dump right here, right? And we're heading up towards Wash Pond and Middle Pond out of the frame. And the shoreline change rate in that area ranges from a couple to more than 3 feet per year. The landfill or the dump, if you're not familiar with it, that's what it looked like after Sandy. That's in 2014. Amber McDonald, my former student for scale, pretty ugly scarp of rusted metal and paper and whatever else. In 2018, the town put in a revetment and graded back the landfill. And that's what it looks like in March. I didn't go out there today, but I'm sure it looks about the same. I won't comment. I'll let you be the judge of how effective that's been. Now, I point out Wash Pond because that's one of our profile locations. And that was purposely cited there because that's one of the areas actually just outside of the highest erosion rate of anywhere on the island we measured in this shoreline change mapping. It's that measured along that red line right here. And if we go to the nearest transects, we see, okay, it's about a little more than 3 feet per year on average. So we'll round that up and call that 1 meter per year. On average, the shoreline is retreating. Now, what the profile data lets us do is actually see when that change is happening. So these are 3 lines up here. The red one, which there isn't much of a dune, this little bump is kind of a baby dune, right? Is the red line was one of our first profiles in 2013. This black line, right, the first one, is January 3rd of this year. And the second one in yellow is January 13th. Now, if you're not in the Northeast in the winter, we had storms in mid-December, January 10th and January 13th, back to back to back. Judy's video was taken right here on January 13th. On the east side, because of the wave direction, not a ton of erosion on the beaches. The west side here, particularly at Wash Pond, got whacked pretty good. And you can see where the shoreline jumps back just in that one storm event. And it's hard to get a sense of scale on these boxes if you're not used to looking at them. It's 5 meters for one box. So it went back several meters in that one storm event. So let's say 10 feet it went back. If we look at it kind of this way, that's showing our oldest profile to January of this year after the storms. And if we look at it, it's about 13 meters of retreat. Now, as a scientist, that makes me happy because what did I tell you the shoreline change rate was? About 1 meter per year. 13 meters, 11 years. It's about the same number. That makes me happy. When I have 2 independent data sets that come line up like that, as a scientist, that makes you happy. What did that site look like before and after? The area around Wash Pond is a very low glacial bluff with some overwash and dune deposits on top. That's before the storm. That's the little sign I'll show you in this image here. And that's the little bit of glacial bluff exposed at that site. Fortunately, right before that storm, we put in a new starting point for the profile further back. So hopefully we bought ourselves about 10 years before we have to do that again. All right. So let's close with my last point. I told you it's optimistic. I'm sorry. We'll leave on a kind of the bummer. Shoreline impacts don't get better in the future. Full stop on that. It just doesn't. This is a bullet, a paragraph, or a couple sentences from a report by the U.S. Geological Survey. Lead author was Ben Gutierrez. This was a working group. It was like 30 of the biggest coastal scientists of the early 2000s got in a room and said, okay, let's put some probabilities on this. Let's kind of talk this all through. And the wording was that virtually certain that headlands, that means bluffs, will be subjected to increased erosion for all 4 sea level rise scenarios. They looked at 4 different scenarios of sea level went up this much or this much. And it was very likely that that erosion will accelerate in response to increases in sea level. The reason that happens is when bluffs are eroded by waves, the sediment that comes out of the bluff tends to kind of plop down at the bottom of the bluff. The sediment that's sitting there, we call talus, is actually protecting the bluff for a while until the waves remove that, and then they can get to the bluff again. It's kind of its own little shoreline protection structure for a little bit of time. If sea level creeps up, maybe we see more frequent or more intense storms, and that cycle happens faster, you tend to see higher rates of bluff erosion. An interesting proxy of that I've started to look at is the Great Lakes. The Great Lakes have very similar glacial deposits, and instead of a gradual rise in sea level, they see sudden rises in lake level. And when they do, bluff erosion increases. So I think it's a good proxy for this process. What about the barriers? Well, I pulled this sentence from a paper by Mariotti and Hind. Chris Hind's a contemporary of mine at VIMS. For my money, he's probably the best I'd say young coastal scientist, but I'm not that young anymore. But we're about the same age, and he's about as good as it gets. And I really like this wording in here that even if sea level, I don't like it that what it says, but I think it's a good conclusion that even if sea level remains at present rates, barrier retreat, that overwash process, will increase by 50% by the end of the century. And that's assuming sea level doesn't start going up faster. So no matter what we're looking at, unfortunately, none of this gets better in the future. I don't have a sudden Pollyanna thing to end on going, it's all good. It's the reality of it. It's the geology being the geology, and we just need to learn how to adapt to it. And with that happy note, I'll leave you with questions. Or do you want to have them on mic for questions? Do you want me to just repeat? Okay, go ahead. Yeah. Yep. But I'll get it. Yeah. Yep. I think with the budget they had and the timeline they had, they did what they could. It's not a judgment against town. It's not a perfect. So I had this conversation about, wind farm and energy production, but it works for everything. There is no solution. There's only compromises. Right. And I think that was a compromise of what they could do. Are there any young kids in the audience that could be slightly off? Okay. It's kind of like sex ed in school, where the only thing that works 100% of the time is abstinence. They always teach retreat's the only thing that works 100% of the time. So ideally, dig it all up, put it somewhere else. But that's a challenge. It's an expense. That would have been the perfect world, right? Dig it up, roll it back 100 yards, cap it back there. But budget and everything else. I mean, I understand why it's, is what it is. Excellent question. Why is West Beach eroding? All right, let me get back to my map slide because I can answer that better with a map. I brought extra slides as I always do, but let me just go back to. I hate when people do this at talks, but I don't have a choice. There we go. Okay. So if we look at where West Beach is, and I'll stand here so I can use the laser pointer on the screen. Right. For those of you unfamiliar with the area, the profiles are up here at West Beach, right? And this is Great Salt Pond, Old Harbor's over here. So prior to 1900, late 1800s, Great Salt Pond would close up periodically. They put in this jetty. Actually, I'm going to cheat. I'm going to zoom in on that. I did this in the earlier meeting. I think it'll work. And they built a jetty to maintain New Harbor. Right? And when they did that, right, how many people have taken a Geo 1 class and know what longshore transport is? Yeah, good. Wow. That makes my day. Like a third of you guys are taking a geology class. I mean, it should be all of you, but a third is good. So longshore transport goes from south to north on that side of the island. So sand grains eroding off of Graces and Dories, probably as far down as southwest, moved to the north, and historically would have gone past that all the way up to North Lighton and out into deep water. Once you build a jetty or a groin that sticks out like that, it traps that sediment. So if you were standing at the Coast Guard station in 1899, the beach was right there. That whole wedge of sediment accumulated afterwards, right? This whole triangle right here. And so what's happening now is a sand grain comes along, gets in the pond, gets dredged out by the Corps, goes somewhere else. And that sediment that used to go up the shoreline is no longer getting to West Beach. So I think it's a sediment starvation issue rather than purely just wave erosion or something changing other than that in the last century. Yes, sir. Oh, so dunes are by definition wind blown. So it's wind. And that's the reason it blows up. It can even form on top of some of the low bluffs where it can blow up the bluff face. Yeah, it's wind blown. And so it comes from the beach. And so, I've got this one up. Our Crescent Beach profile, right, is down by the pavilion, right? And it's getting sand mostly from the intertidal beach. So the the dry beach in front of the dune on a windy day blows towards the dune. And so your best wind directions happen when things are coming in at an angle because you've got more beach for the wind to blow across, and it's transported onto the dune that way. The reason it takes so long to recover a dune is the processes are completely different. The beach recovers from waves and tidal currents. The dunes only really recover from wind or dump trucks of sand, right? But it's because it's wind. Yeah. Yep. Yep. Yes. Okay. So let me put my triangle back up. So where would the triangle be skewed more towards surface water and groundwater? Wow, that doesn't fit. It's a window. There we go. Where the bluffs are really high. So after Sandy, we did a look. Amber McDonald, my student, I did a thing where she pulled profiles from the LiDAR. I'm trying to remember the details because it was 2015. But every profile she measured, which is a cross section she takes of the bluff, every bluff lower than 10 meters, so every bluff lower than 30 feet, eroded back directly during the storm from waves. Every bluff taller than 15 meters, the toe of the bluff went back, but the whole thing didn't come down. And so I don't know whether that's a perfect number, but where the bluffs are tall like that is where the surface water and groundwater is playing a bigger role than where the bluffs are fairly low, right? They're impacted more frequently by waves and it's eroded more frequently by waves. So I don't have a perfect number on the height, but certainly on the south side, you see deep gullying. On the north side, you see it at Clayhead. And then the type of material probably plays a big role as well. Some of them are really prone to moving by surface water. Some of the really hard clay stuff probably doesn't move that easily with surface water. It tends to, we've seen it a couple times, dry out, crack, and then just fail all at once when it got really wet. So it's probably a combination of material and height. But I don't have I can't say this is your best example of, yeah, it's a great question. Drew and I are slowly trying to work on some of the process stuff with the drone imagery. I said it earlier to me, he's really backlogged. And so I'm trying to slowly kick him in the butt to get him moving on it. So stay tuned and hopefully, yeah. 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 The intertidal zone in a lot of spots there is really coarse grained, like a lot of boulders in the surf zone, and it's fairly flat boulder terraces. I think that deflects it doesn't deflect, is the wrong word. It dissipates some of the wave energy that can't get directly to the bluff with as much force as it can where there aren't big boulder fields in front of the bluff. I think that's the best we've come up with so far on it. I don't think there's a big difference in material or any composition of the bluff that we've seen. I think it's just the geomorphology of the surf zone just diffuses enough energy that it's not quite as dramatic. Yeah. Yes, sir. Yes. 100%. Yes. Yep. So the original composition of the glacial deposit had more boulders in it in that case. Whether it's so the question is why are all the boulders there? Well, first, your observation is 100% correct. The boulders you see on the beach used to be up there, right? And there's a couple of what we call widowmakers hanging out up top there that we want to make sure people aren't playing around. The glacial deposit there just had more boulders in it. Whether it's a piece of an ice stream or something where the boulders got concentrated, I don't know. It's just the way to think about the island is it's a bulldozed pile of sediment. And so over here, you might have more clay rich stuff. Over here, you might have more bouldery rich stuff. And I think it's just kind of happenstance. There's a bunch there. Yeah. Purple shirt. And then I'll go to Nigel. Yes, sir. So yeah, the question is, should we keep building up dunes in front of Corn Neck Road, or will the island slowly become two? So if you've read Les Serkin's book, it's great, Block Island Geology, if you can still find it. Les and I disagree on that. I don't think the island splits in two in any reasonable time frame if we allow it to continue to evolve and erode. if you want to put the sand in front of the revetment to make more dune habitat and offer some protection for the road in smaller storms, I don't think there's a geological objection to it. I don't think that stops the road from being eroded during Sandy at the scale that's being done now. Right. But I don't have a big concern about the island splitting in half on the human time scale. You look at a couple millennium, all bets are off geologically, but I think you're okay for a few decades. Nigel. Okay, I'm just pulling up my other slides because I had one in there to talk about that. So hold on one sec. So the question is about how these barriers, particularly the small pond barriers, will evolve over time. And I'm trying to find my middle pond picture. Sorry. Again, I hate when people do this at conferences, but I am going somewhere with it. So one of the things they do, and this isn't the slide I'm looking for, but this is Middle Pond. Middle Pond's a very small coastal pond on the northwest side of the island, before you get up towards North Light, but north of the landfill. And what I highlighted here, I think if I turn on my slideshow, is I pulled the imagery before and after Sandy. So that was before Sandy. That was after. Not a huge change, but if you sit and look for a second, right on that red line, you'll see a little bit of white on the backside. That's sand. It's not vegetated yet. And that's one of those washover fans that went down into Middle Pond. And we went out and surveyed on it, and it's definitely was a washover fan. And then the barriers continued to retreat. And what I did this exercise for a couple of reasons. One, I had a feeling Middle Pond would come up. But you can actually see if you look at my inset, if I zoom in right here, I think when I go pre-Sandy to post-Sandy, you can actually see how the dune retreated. So I'll put my cursor right there. It's not gone away, but it retreated back several, maybe 5 meters. And that was largely the crest of the dune got removed and the sand got pushed back across the barrier. Again, that's that overwash process I mentioned. Now, all this stuff down here, that's actually related to the 38 hurricane. And if I could do a better job of figuring out where the hell I put that picture from my other talk today. Oh, here we go. Hold on. That's Middle Pond in 1939. Anyone want to hazard a guess when that inlet formed? Yeah, 38 hurricane. So what's the future? They continue to overwash. The barrier continues to move, in this case, move east. And pond essentially gets smaller, except at the same time, sea levels rising and flooding new parts of the back barrier. So will it go away? Maybe if sea level rise is too slow to flood the back barrier fast enough. I mean, Wash Pond to the south probably looked like Middle Pond a century ago, and it's gotten a lot smaller. So it does change over time as those barriers migrate. But new areas are getting flooded with sea level rise. New salt marsh is being created, so maybe it balances out somewhat. It's a good question, Nigel. I mean, these are good case studies. We leave them alone. This is what barriers. Again, what's their mantra for yoga class? Landward and upward. Move back, move up. Judy. Probably one big one with a lot of small ones. No, a lot of little perched aquifers with one big one, I think is probably the, wrong. Call Ann Vieger for that one. Yeah. Yeah, for the most part. So the question is, are the rates similar on Martha's Vineyard and Nantucket, and is there collaboration? It's the second part first. Collaboration only in that I drink beer with those scientists at conferences. But yeah, from what I've seen, they're comparable. We're not seeing anything more extreme here. The eye-opening one is always West Beach because it's on what you think of as the lower energy side of the island, but it comes back to the sediment starvation issue, I think. But if I know, I was making sure we weren't suddenly under attack from pirates, you know? I think that, yeah, anyways. Yeah, in the back. Sure. Can I ask clarification on the dunes or the bluffs or both? Okay. Okay. So I'll start with the last one first. Geologist. Listen, I will say I've worked with enough ecologists. Any invasive species we remove and put in a native plant, I'm all for. So fine. As far as vegetation on bluffs probably help with some surface water runoff. They probably, if they're down low on the bluff, breaking waves probably don't care if there's plants there. Right. But if it's up high, it can help with that. But I've seen some really expensive projects out on the outer Cape where they grass the whole dune slope. And you know what? Or the bluff slope, it didn't do a whole lot. So, you know, yeah. If you go along Wellfleet sometime in a boat, you can just see these green stripes where they've paid to grass the whole thing. And yeah, it's trees actually do better when they fall down because when they sit at the base of the bluff, they can actually add some protection. And they do that in Maine on the river bluffs where they'll actually leave the tree falls for exactly that reason. But again, up there, I don't think the waves care. And they'll just scour around it and then the tree falls down. So, yeah. I do run a calculation called the profile. Oh God, what's the acronym? SVI. I stole it from the Australians. But basically it takes the reading that month and compares it to the long-term average of the profile. So you can see if you're kind of on the upper side or lower side of that. I haven't done that just for the dunes. It's a good question, although for most of it, it's going to be a slow, steady up. But on the beach itself, we do that. Profile vulnerability index, that's what we call it. And it takes it around the mean and you see where it's a little lower or a little higher. The shoreline change maps would be a better source of maybe identifying areas where the rates are lower or higher. And they pick spots off Crested Beach and they dump it now. So yeah. George.
The question for the whole audience, just to go back to what you mentioned, shoreline change. Again, where can people find those?
Okay.
And then two, the relationship between the shoreline change map and the bluff change is important because it's very similar.
Yeah.
I want to go look them up myself.
So I'm going to show you two places you can get it. So one of the clearinghouses that's not super updated was part of the Rhode Island Shoreline Change Special Area Management Plan. I was one of the project geologists on that, or I was the project geologist on it at the end when John died, John Boothroyd. And in here, there's a whole bunch of information, but if you go up here and the website, if you can't read it, is beach, like we go to the beach, samp.org.org. You can get the same maps if you just Google Rhode Island CRMC, Coastal Resources Management Council, because the maps themselves for the shorelines become regulatory documents. Coastal setbacks are based on this average erosion rate. But if you come to coastal erosion maps, and I'm crossing my fingers, but I think Block Island's on here, on the interactive one. There's an interactive one that worked last time I checked it. And a little pop-up says exactly what I just told you today. Shoreline change doesn't happen linearly. It happens in big jumps. And don't hold us responsible if your house goes away. No, doesn't say that. And now that I'm thinking, I don't think Block Island made it into that version. So I'm going to go to a different. So if you're on the mainland, you can look this up. Let's go to RICRMC because this is where the real maps live. And if you Google RICRMC and you come up here under maps, there's lots of cool stuff, but you'll find storm tools, which is the flooding map or model I showed you, which was done by my colleagues at URI Engineering. And then there's shoreline change maps. And if you click this little map viewer comes up and you can click wherever you want around the island. I will try it, but it's a long, they're big files. We'll see if it opens. They will open it. They're not faulty. It just takes a while because they're big files. There we go. Don't get impatient, Brian. It's working. Stop it. And these come up at like 42-inch wide PDFs. They're a lot of work to make, which is why we haven't updated them in a few years. But if I go to 100%, I'm not doing that just to show you my name. That's not intentional. I'll scroll down. But you can find these transects anywhere you want around the island. And again, in black is the actual amount it's changed for the shoreline, the black and green line down on the beach, right? 1952 in black, 2016 in green. We don't use the same 1886 map because the state has always used these imagery. And so we just use the aerial photography. And you can get a sense for the shoreline change. Now, there aren't similar maps for the bluff. Maybe someday we'll get to that or we'll get asked to do that by CRMC. But the shoreline change rates from what we've looked at are a pretty good proxy for that, right? We talked about it being a foot per year of the bluff. You start looking around here, you see similar numbers. So at least over this 5 or 6 decade kind of time scale, the numbers kind of come out about the same. So if you're interested in how fast the bluff's retreating, the shoreline change maps are probably a decent substitute for that. Yep. But beachsam.org has all the storm tools flooding, which is kind of fun and kind of scary to play with. So it's there as well if you want it. And I mean, you guys can put it on your Facebook or something if you wanted to. Nigel. Mhm. Yep. Ash Wednesday, 1962. We can keep going down the list. Here's the thing. If I had LiDAR data from 1937 and 1943, I'd see a really high rate of change for the same reason. I'm looking at that steeper curve because it's a short period right after the storm. So I think you'd see the same thing if we had the data to show that. Right. That's my supposition, but we don't have LiDAR. I don't have the detailed data to do that. I don't think it's a background signal of anything else. I don't know if we could tease that out on that kind of short time scale. At least not with any confidence. Right? I could arm wave, but. All right. Thank you.
Well, we went, no. Thank you for coming. Whoop. Now I'm going to fall over the cord. As Brian did such an able job in discussing who our speaker will be next week, please come and hear about surf casting over the years on Block Island with his friend Dennis Zambrata. And Brian, thank you so much. And look at those maps. They're cool. Anyway, thank you very much.